So it's my pleasure today to introduce you to Christina Peters, also Tina. And so she has a BA in physics from Goshen College in Indiana, where then she went on to do a PhD at Drexel University in Philly, where she got a PhD in physics. So it was exploring the quasar luminosity function with quasars selected by both color and variability. So this was clearly an astro-heavy project, where then she went on to a postdoc at a very good cosmology institute, the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto, where she was working with Professor Renee Hlozek. So from here, she switched over to working at the University of Delaware within the Department of Computer Science, Computer and Information Sciences with Hagit Shatkai. And this was starting August of last year. And she got involved in a project more or less trying to figure out what are the missing methods in data science and machine learning for physics applications, whether it be, well, astrophysics or beyond. And that's, I guess, the lead in to the talk. I don't know if I missed anything.
Thank you very much, Chris. So as Chris mentioned, my background is in astronomy with lots of work relating machine learning to problems in physics. And in this presentation, I'm going to tell you about applying machine learning techniques to the problem of reconstruction in particle physics. So this project is part of the DIDAX collaboration, which includes scientists and engineers, physicists, computer scientists from the University of Delaware, Rutgers, and Rice University. So let me jump right into it. The motivation behind this being the problem of uncertainty. A lot of different machine learning methods are used widely throughout the physical sciences, whether that's astronomy or particle physics. And many of these algorithms can provide a locally optimal solution or sometimes the most probable solution, but often do not provide some sort of uncertainty or a full posterior over the quantity that you're interested in. In general, in experimental science, uncertainty is necessary in order to compare different measurements. If you're interested in how precise your measurement is, as well as how accurate it is, you're definitely going to need some uncertainty on it. As a case study today, as I said, I'm discussing reconstruction of particle interactions in particle detectors. With this problem of reconstruction, these physical processes occurring within the detector, such as a dark matter particle interacting, are inferred from things that you can observe within the detector, such as the things you want to infer, like the particle type, the energy, and the position at which that interaction happened. And this reconstructed position is key in things like reducing the background of your detector. And so you'd want to have something like the uncertainty on that position in order to have a good idea of your background. And this reconstruction is commonly done with machine learning techniques such as neural networks. And most of these techniques cannot provide an uncertainty or a posterior distribution over that reconstructed position. So within the DIDAX collaboration, we've been exploring how to use probabilistic graphical models to this problem. So first, I'm going to give you an introduction to probabilistic graphical models. For this introduction, I'm going to use an example system that I've been calling is the dog out. So in this system, we have 4 different components to it. There's a gate, a cat, a latch, and a dog. The gate is the back gate open. The back gate is open. The cat is playing with the gate. The latch is the latch on the gate, so is the latch loose. And then there's the component, the dog. the dog is out. So let me go into a little probability terminology. So these 4 components in our system are called random variables. So random variables are G, C, L, and D. And we have the random variable is a function that maps some event to its possible values. And the set of possible values for each random variable is over some range. That's the range is the set of variable values that it can take on. So a range of values could be discrete, such as true or false, heads or tails in the case of a coin flip, or 1, 2, 3, 4, 5, 6 in the case of rolling a die, or 1 to 20, depending on what kind of die you have. They can also be continuous. In this case, an example of a continuous variable would be like the angle at which the gate is open. So the gate could be open at any angle from a range of 0 to 90 degrees. So in our toy example here, each of our random variables, the cat, the gate, the latch, and the dog, have a range of just true or false. So there's just 2 possible values for each of our random variables. Okay, so now some graph terminology. So our graphical model is made up of nodes and edges. Each node is a random variable. And as I just mentioned, they can be either discrete or continuous, and they're connected by an edge. So the edges creating the connections between the nodes indicate that there's a dependence between those 2 nodes. An arrow in the graph can indicate that there is believed to be some sort of causality between one node and another. And we'd call, in this case, x1 the parent node and x2 the child node. This is a graph that has arrows is called a directed graph. And you could imagine a directed graph where you could start at a node and follow the arrows all the way around and end up back at that same node. And that would make a cycle. And an acyclic graph is a graph that doesn't have any of those. It contains no cycles. So a directed acyclic graph is a graph with arrows, but no cycles. And this is the type of graph that we'll use in this toy example and then in the graph for the position reconstruction. Okay, back to our dogs and cats. So if we think that these 4 components in our system are related, then our initial guess for the graph may be that each node is connected to every other node in the graph, right? Everything in this system interacts with everything else. However, one asset of a graphical model is that it can be simplified based on some conditional independencies in the graph. So let's think about this in our example. Let's think about, for example, the dog, the cat, and the gate. Perhaps it's reasonable to think that once we know whether or not the gate is open, the dog being out is no longer influenced by the cat. So I would propose we remove the edge between dog and cat. Similarly, we might think it's reasonable that once we know whether or not the gate is open, the dog being out is no longer influenced by the latch. So I'd propose we remove the edge between dog and latch. We could state this belief as dog is conditionally independent of cat given gate, and dog is conditionally independent of latch given gate. This probability terminology I'll discuss a little bit more later. But based on our knowledge of cats and dogs and latches and dogs, we propose we remove those 2 edges. Additionally, we would think that cat and latch are independent of each other, right? Those 2 things don't really interact. We expect that cat is not influenced by latch and latch is not influenced by cat. So we could remove the edge connecting them, but we should also think carefully about it, that cat and latch are also dependent given the value of gate. For example, if gate is true, it is more probable that cat is true, and it's also more probable that latch is true. So we would say that these are conditionally dependent given our knowledge of gate. So here's our sparse graphical model. And then I want to add some arrows based on my belief of how things are interacting. So the latch is loose, and that's directly influencing gate. They're causally related. And then cat is causally related to gate as well. And then gate is causally related to dog. So the dog sees that the gate is open and runs out. And it doesn't really know about latch and cat, but it is influenced by latch given gate. I'm going to pause here in case there's any questions about this toy model so far. Okay. So a little bit more terminology. Let's talk about an event. If each of our random variables could be assigned a possible value. So our random variables are typically denoted by a capital letter, and then their values are typically denoted by a lowercase letter. So capital G for gate and a lowercase g for a possible value of gate. And there we go. And so this is a case where an event is where we've made some observations of our system and assigned one of the possible values within the range to each of the random variables. And so in this case, a possible event is that the cat is messing with the gate, the latch is not loose, the back gate is open, and the dog is not out. So that is an example of an event in our toy system. Now, each of these random variables also has an associated probability distribution. So this is a function that maps a random variable to a value between 0 and 1. So for a discrete random variable, the probability distribution will also be discrete. You have a coin flip where if you have a fair coin, it'd be 1/2, 1/2. If you have a weighted coin, it'd be the probability of heads. And then the probability of tails would be 1 minus that, as a probability distribution always has to sum to 1. For a case of a fair die, it would just be 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. For a continuous variable, a probability distribution would often be something like a Gaussian distribution or a uniform distribution, where it also has to sum to 1. Okay, one final bit of probability terminology. For a conditional probability is a probability given some information or some evidence. So in this case, we would write the probability of some random variable given, that's what this vertical line is. In this case, the probability random variable is X, given some evidence, that's a capital E, the evidence variable. You'll just also hear this called a posterior probability, or just a posterior for short. This is just the probability of all the possible results of the experiment, where both the random variable X and the evidence random variable are both true, divided by the probability for all of those results where the evidence variable is true. Now, this is important in the context of graphs, because when I draw an arrow from one node to the other, so for example, this node gate to the node dog, I'm saying that the state of my random variable dog depends on the state of my random variable gate. So the probability distribution for the random variable dog depends on the state of the random variable gate. This is true in general. So the probability of any node given its parent's node, given its parent or parent's node, is the probability distribution associated with that node. A couple more things about the probability distributions. A random variable is independent. So some random variable X is independent of some random variable Y if the state of Y does not influence the probability of X. So this would be completely independent. In general, this isn't interesting. Like, we wouldn't really have a system that we wanted to study where some node is completely independent of the other variables in that system. What we really are interested in studying is this conditional independence. That's the bottom case here, where we have two random variables are not independent, but they are conditionally independent given some third variable. So that means if the third variable is observed, then like we know its value, then the values of the first two variables are no longer dependent. So this is exactly what's happening when I proposed we remove the edges between, remove the edge between cat and dog, or the edge between latch and dog. So we're saying that dog is conditionally independent of cat, given gate. So I've written that there on the bottom. The probability of the random variable dog and the random variable cat given gate is just the probability of dog given gate and the probability of cat given gate. So this conditional independence is these conditional independencies within a distribution is what allows us to represent a distribution, a probability distribution, in a very compact way as a graphical model. I'm going to pause here again in case folks have questions about all that probability jargon. Okay.
Oh, someone unmute. I don't know. Lee Barnby. Okay.
Okay.
Unless it was, I think it's been clear.
Right. So what can we use this graphical model for? So in general, the model shows the components of the system which are directly dependent and conditionally independent in an interpretable way. So we can write down in a way that is both compact and not opaque the direct dependencies within our distribution, the directly dependent dependencies within our distribution, and then the conditionally independent ones by leaving out edges. Additionally, the graphical model is a representation of the probability distribution over all of the random variables in the system. So the full joint distribution, but in a compact way. And finally, most importantly for moving forward and what I'm going to talk about, we can query, that means like ask a question of our graph, given some observation we've made of the system. And I'm going to move back to our toy example real quick to give an example of how exactly you would query or ask a question of a graph. So if the dog is out, what is the probability that the cat was playing with the gate? Writing that as an equation, that's the probability of cat, that's the random variable, given dog, and that's lowercase because that's an observation of the random variable dog. What is that equal to? This is an example of inference. The terminology for inference, I'll go over really quickly. So we have observed some event. In this case, the dog is out. And so that's our lowercase e here, the evidence variable, but it's observed, so it's lowercase e. And we want to compute the posterior probability distribution for some query variable. In this case, the query variable is cat, was the cat involved? And then there's all the rest of the random variables in our system, the non-evidence and the non-query variables. And so at the bottom, there's the equation of how we would calculate this. The probability of our query variable, given our observed event, is equal to alpha, that's just some normalization constant. And then we sum over or marginalize over all of the possible values of our non-evidence and non-query variables for the probability over our query variable, our observed event, and those non-evidence and non-query variables. So in our toy example, our query variable is cat, our evidence variable is dog, and then the gate and the latch are our non-query and our non-evidence variable, and we've observed that dog is true. So we're just summing over latch and gate for the probability of cat and dog and latch and gate. Now, in order to actually perform this calculation, we have to assign some probability distributions to each of our nodes. In this case, I'm going to consult some expert, myself, on dogs and cats and gates and latches. In actuality, and what I'll discuss further on, usually you want to learn these probability distributions from some data. But I don't have data on dogs and cats and gates and latches, so we'll just assign some values. So for cat and latch, we just have some prior that the cat and latch are true. I show here at the top. in the middle for gate, we have a table of possible values given all of the possible values for cat and latch. And then at the bottom, we have a table for the probabilities of dog given the values of gate. So these are just assigned values. I didn't conduct any experiments to determine them. And then I'm going to calculate the probability of cat, the cat playing with the gate given that the dog was out. In general, this is just some tedious arithmetic. So here the probability that cat is true is shown on the top left. The value I get is 0.05, and the probability that cat is false is 0.14. So the probability, the posterior probability distribution over the cat playing with the gate, given that the dog is true, is shown there at the bottom after we're normalizing. So the distribution sums to 1. One thing I want to note here, other than that this was fairly simple and tedious for this example, is that as the graph becomes complex or our random variables have more than 2 possible values, this calculation actually does become quite computationally expensive. Right, I'm going to pause here because next we're going to leave the toy example and actually move on to quantifying reconstruction uncertainty for particle physics. So any questions about probabilistic graphical models in general, or dogs and cats? Yes, alpha is a normalization constant that is just summed out when we normalize the distribution to 1. It is in the denominator, it just comes from summing over the probabilities over dog. Okay. So now I'm going to discuss how we actually apply this framework. Sorry
to interrupt. There was one more. Does it have a fixed value? Was a question in the chat.
No, it doesn't have a fixed value. It'll depend on each system and on these probability distributions for each variable. But it'll be in here in the sum here. Alpha is the same for the probability of cat given dog is true, and the probability of not cat given dog is true. And so when you normalize, they just cancel out. So it could be calculated for each particular system and each particular query that you have, but you don't have to calculate it because it'll just come out in the division. Did that answer the question? Okay. So now we want to discuss how we can apply this framework that we've just learned of probabilistic graphical models to reconstruction of particle interactions within a detector. So the detector we're considering here is xenon 1 ton, which is one of the detectors in the xenon experiment. So the xenon experiment has the goal of detecting dark matter particles by measuring the light that the particle interactions produce when they interact with the nucleus of a xenon atom. So in the xenon 1 ton detector, it's essentially a large tank of xenon with sensors that detect the light at the top and the bottom. So less generally than that, the detector is a dual phase time projection chamber, where I'm showing a schematic of it here. So the particle interactions entering the tank, or sorry, a particle entering the tank interacts with the xenon atoms in the tank. And in that interaction, it produces UV light and some electrons. The UV light is detected by the array of sensors at the bottom of the tank, and they call that the S1 signal. And then the electron is drifted up to the top of the tank where there is xenon gas. In the gas, the electron interacts and produces light again, and this is detected by the sensors on the top as an S2 signal. So these sensors are photomultiplier tubes, and they're arranged in arrays on the top. And in the top, you can see they look basically like concentric circles with one in the center. And then the sensors in the bottom are arranged more in a hexagon, like you can see there. The S1 and S2 signals produce what are called hit patterns, which are generally the number of photons detected by the PMTs integrated over a short period of time for each interaction. And these hit patterns are basically the observables that we're going to consider moving forward. Now, with the data collected by this detector, it's possible to identify the particle type, to reconstruct the energy, and to do a three-dimensional reconstruction of the position. In this example, and using probabilistic graphical models, I'm just going to show an example of one-dimensional position reconstruction, where I'm only going to consider the S2 signal and the hit patterns that it produces only on the top array of sensors. And the data I'm going to use for that, for the training data to learn the graphical model, is simulated xenon 1-ton data for a fixed number of electrons. So first, I'm going to discuss how this simulated data that I'm going to use was processed in order to learn a probabilistic graphical model where I'm only using discrete random variables. So instead of the fancy schematic that I just showed you, I'm going to show you this very simple one, where I'm going to consider separately the tank of the detector, where I show it on the left in cylindrical coordinates, and the top array of sensors that I'm showing here on the right in circular coordinates. So the positions of the particle interactions within the detector are known for our training set of simulated data. So here I show two interactions within the tank of the detector. For the 1D reconstruction, we're going to consider only the row axis, so like the radial position within the tank of these interactions. In order to have a discrete probabilistic graphical model, I'm going to divide the tank into regions based on the row axis. So you can think of these as basically like tubes within the tank. So those two interactions I showed on the left, I'm kind of showing here on the right, one towards the center and one towards the edge. And I'm going to have 12 radial regions. And each interaction is assigned a label basically from 1 to 12, going from the number 1 is the most is the closest to the outside of the tank, and number 12 is all the way at the center. And these labels indicate basically the region within the detector at which the interaction occurred. So the sensor observables in our training data, as I said, are the hit patterns for the top array of the detector. And here I'm showing two different hit patterns, one where the event happened more towards the outside of the detector and one where it happened more towards the center. So first, I'm going to simplify this detector array from 127 PMTs down to just 6 groups. So I assign them to groups based on that radial position, the circle of PMTs all the way towards the outside, or one group, and then they're assigned basically in concentric circles going in. And then the intensity of a group of PMTs is simply the average over the PMTs in that group. So the two hit patterns I showed previously are now shown here, where all of the PMTs in a group have the average value of the individual PMTs assigned as the intensity of that group. In addition, I'm going to discretize it as I did for the positions of the event interactions. In this case, there's 20 different discrete intensities that a group of PMTs can have. So they're just assigned a value from 1 to 20. So now our system for the xenon 1-ton detector has 7 random variables. These are going to be the nodes in our graphical models. So I have group 1, 2, 3, 4, 5, 6, which are representing the groups of PMTs in the sensor array. And then I have node R, which is the position at which the interaction occurred within the detector, which is the radial position within the tank of the detector, which has a possible value from 1 to 12. Any questions here about what I've done with the simulated data from Xenon 1 ton? Okay. So now, oh, I see one. The angular information. So I can certainly do this with angular information, and I have done a bit. I don't have any results to show from that yet. And then eventually the goal is to do both the radial and the angular simultaneously with a more complex graph. So our goal here is to learn the structure of this graphical model with these 7 nodes. The 6 representing the groups of PMTs and the 1 that represents the position of the events using our training set of simulated 1-ton data. What I'm going to do next is proceed to gloss over something that is actually quite complex, which is how do we go about learning this model? So if you recall from the toy model with the dogs and the cats, I just consulted an expert myself and wrote down the model and wrote down the probability distributions for each node. In actuality, I want to learn this from data. And so determining the optimal structure is essentially a model selection problem. So the first thing I do is define a scoring function. In essence, the scoring function rewards an edge or edges or parent nodes for each node based on how strong the dependence is between those 2 nodes. So score goes up if dependence is stronger, or I should say the stronger the dependence between 2 nodes, the greater the score that edge contributes. And you're summing over all of these dependencies in order to determine the overall score for a graph or for the graphical model structure. And in essence, what you're doing is searching over the model space for the highest scoring network you can possibly find. This is much more complex than what I just said, and it is a topic for another longer talk. One other thing I want to mention is that if you are searching over the space for the highest scoring network, you may end up with an arbitrarily complex graph that is more complex than what you actually need. And so one component that goes into this is a penalty for unnecessary complexity or for too much complexity in your graph so that you don't end up fitting noise. So here is an example of a simple graph structure that is not the overall optimal graph structure for Xenon 1 ton, but is a pretty good fit to what's happening. And here we have that the different groups of PMTs are connected via edges to the groups that are adjacent or close to them. And then the node that is representing the position of the interaction is apparent to both of the groups that are in the, I shouldn't say the middle, but are not the edge or the middle groups of PMTs. So this is an example of a graph that could be used to represent the hit patterns and the event positions in this simulated Xenon 1 ton data. I'm going to show some examples now of what the probability distributions are for a couple of these nodes. So here's a representation of the probability distribution for the node that represents the event position. So if you remember, there's 12 discrete values for event position as a function of the radial position within the tank, where 1 is the outer, so all the way on the left is the outermost position, and then 12 is all the way at the inner. And so if you remember from our toy example, the cat and latch at the top of the graph, they were similar to this R node in that they didn't have any parent nodes. So this is essentially just the prior over the position of the interaction. We're essentially what we're recovering here in this probability distribution is the number of interactions that happened in that region within our training set. So you can see the highest probability is region 2, where that is where the region in which the largest number of interactions happened. And region 12, all the way in the middle, has the fewest number of interactions, simply because it's the smallest region within the detector. So for a more complex example of a probability distribution, here is the probability of the node G4 or group 4, which is shown in green in the bottom left here, of the nodes of the detector. Sorry, the PMTs within the detector. And on the graph here on the right, the intensity of group 4 increases as we go from left to right across the graph. And the only parent node of G4 is R, which is the position node that we showed the probability distribution for on the previous slide. And so here we're showing the probability of G4 having some intensity based on the value of R. So for example, let's say for an event where the interaction happened in the very outermost region of the detector, that would be the very top of this plot on the right, the outermost region. The colors here indicate the probability of G4 having a given intensity. So that probability peaks around an intensity of 5 or 6. Or if the event happened at a position more in the middle, not in the innermost or the outermost, but somewhere in the middle of the detector, there's a much higher probability of G4 having a high intensity, or an intensity of 19 or 20 out here all the way on the right. And this should intuitively make sense to us because G4 is the group of PMTs that are around that position within the sensor array. Any questions here?
There's one in the chat. If you can, do you want me to read it for you?
I can see it. How would G2 affect G1?
What I'm trying to say is, so this usually means some causal relationship between different variables, right?
Mm-hmm.
So the value of G2 somehow affects, so causally creates value of G1, right?
Right.
For me, like this, like everything is affected by just R, right? Where interaction happened, it affects all the detector values. And you're saying that like the value in one PMT affects the value in another PMT. So this is kind of a little, you can figure it out.
Right, I agree. So I wouldn't say that the value in G2 is causing the value in G1. In this structure that we've recovered, we're basically saying that there's there's a higher dependence between G2 and G1, or G3 and G1, than there is between R and G2 and R and G1.
Okay, so it's like a data-driven thing.
Exactly. Yeah. This model was found to be an optimal fit to the training data, and not one that was written based on our understanding of the cause and effect of these nodes.
Got it. Got it.
Right. Okay. Any additional questions? And so let's review real quick inference, or querying or asking a question of our graph. In this case, we want to do reconstruction of position based on our sensor observables. So our sensor observables are the PMTs within the top array. And so our evidence variables in this case are the 6 colorful nodes. And then our query variable is the position node, the gray node. In this case, we do not have any non-evidence or non-query variables, but you could, for example, have dead PMTs where you don't have a measurement. And in that case, that would be a non-evidence or a non-query variable that you would then want to marginalize or sum out of your query. So we're going to calculate the probability of the position node R given some observations with the PMTs with our evidence variables. So in this case, I'm using a subset of the same simulated Xenon 1-ton data as my test set, which is separate from the training set that I used to learn the graphical model, but from the same set of simulations. So some results of our inference here. So this is just for 10 particle interactions, or 10 data points within our test set. So on the each interaction is shown as a panel here in the plot on the right, and then the probability of R is the y-axis, and then the 12 different possible values of R are shown on the x-axis. So in the topmost panel, you can see it's pretty inconclusive as to whether the particle interaction happened in region 6 or region 7. And then the 2 interactions shown on the bottom, it is pretty certain that it happened in region 2, or pretty darn certain that it happened in region 9. So this is an example of the probability distributions that we get out from querying this model. These are very strongly peaked distributions, which I ascribe mostly to this being simulated data that doesn't have a lot of complexity to it yet. So these are the types of posteriors that you can get out of a probabilistic graphical model in this case. I'm going to conclude my talk by not talking about the uncertainties and just showing how accurate these particular reconstructions are with a simple, like, most probable case. So for the most probable case, I'm just going to take the peak of the posterior as the most probable region for each of the interactions in my test set. And then I'm going to compare that most probable region to what I know the true region to be, because this is simulated data. So I'm going to show the confusion matrix here, where on the x-axis is the true region at which it occurred, and the y-axis is the most probable region that it was reconstructed to be at. In this case, with 12 regions within the detector, it was reconstructed into the true region at about 72% accuracy, and almost all of the inaccurate reconstructions were in adjacent regions. I think the regions where it performed most poorly were the outermost and the innermost regions of the detector. So any questions about this before I move on to my conclusions? Okay. Oh, I hear somebody.
Just a comment from the science side. So typically in Xenon, what we really care about is the tails of these reconstruction distributions. So being able to actually show that the tails are small is very impactful in the science. And being able to evaluate the posterior, say that the probability that something happening far away from your fiducial volume for the particle physicists here, the probability that it actually was in the fiducial volume or not. This type of reasoning is not very common in well, particle physics without doing much more computationally expensive things.
I see your question. Can you elaborate on it a little bit? Don't quite understand. How to get the data that was used to learn the graphical model? Oh, how is the data generated, or how is it?
You can do this one at the end.
Okay, sounds good. So I'm just going to wrap up with the conclusions. So as I introduced at the beginning, many of the machine learning algorithms used throughout the physical sciences and astronomy or particle physics can provide a solution, such as a local maximum or a most probable solution, without having uncertainties. And this uncertainty is necessary in order to compare measurements or compare predictions from different models. Probabilistic graphical models are readily interpretable and can be used to both model the uncertainties within a system and make predictions with uncertainties, such as producing a posterior over the variable that you're interested in. Within the DIDAX collaboration, we've been working on exploring how these probabilistic graphical models can be used for reconstruction of particle interactions, specifically within the context of direct detection of dark matter in the xenon experiment. And I hope I showed you that some of our initial results using the simulated xenon 1-ton data show that we can use probabilistic graphical models to compute a posterior distribution over the event position, at least in 1D in this example. And thus we're able to do position reconstruction that gives you uncertainties using graphical models. Thank you. Any questions?
So I'll clap on behalf of everyone, since it's always a bit hard in these virtual settings. So can people first raise hands, and then we can go to whatever gets posted in the chat. And first up is Gordon.
Hey, excuse me. That was a really terrific talk. Thanks for taking the time to prepare it. I really enjoyed it. I love the graphical, the probabilistic models, and I loved your example. And your example is what leads me to the question. I think it was slide 55. It was the correlation matrix you saw with the green band that was diagonal. Yeah, that's it. 55. Sorry, it's 57. Yes.
Right.
Yeah. So we had to do something very similar to this, where in one of the particle physics calorimeters, we wanted to know the starting position of a energy deposit. So instead of building a probabilistic model, we used basically a neural net and used it as opposed to a classifier in regression. So it gave us a number, it gave us the radius where the energy deposit started. Then in order to form this, what we just did was we took the truth, the Monte Carlo, ran it through the neural net, looked at the position it came up with, and then just plotted a 2D scatter plot. And then we looked at the width of the scatter along this diagonal in order to come up with basically our error. So I was wondering, what is the difference between what you've got here and what we did there?
Okay, I think I understand. So I think you were saying yours was a regression problem, right?
Yeah, we treated it as a regression problem, but I think we might have been solving very similar problems here. But so I could be wrong.
I think the primary difference is that this is using like a discrete values. So it's kind of like a classification problem rather than a regression problem. And so a confusion matrix like this is often used for a classification problem where you have two or more different, two or more classes, and you want to evaluate your performance or evaluate how accurately you classify.
If I can jump in as a translator, maybe, I think you want to go to your slide before.
Okay.
Actually, the one you initially went to, because when you're, so Gordon, when you're running a neural net, it just gives you one value normally. If you're just running some like standard neural net, this, instead of giving you one value, gives you a posterior distribution. So you don't have to play any tricks or sort of, this actually quantifies the uncertainty. So you're not having to run many events through some neural net and then estimate, oh, what do I think the error typically is? Because that's something you're doing in a set of many events. This gives you per event uncertainties.
Mm-hmm.
Okay, so this effectively, you did both steps at once. Your training recorded much richer information than the neural net regression did. Okay, that makes it clear. Thank you, both of you. And again, great talk, and thanks a lot.
Thanks for the question.
So if there are other questions, people can raise their hands. Otherwise, I don't see anything new in the chat. So, well, thanks for the talk, and everyone for coming and attending. I just want to thank the speaker one more time. Everyone's muted, so you can't hear the room full of applause, but thanks. Oh, okay. I see clapping. So that was it. I hope everyone has a good day.